As long as humans have been able to talk, they've been able to sing. Not well, though. So tuning systems were developed by almost every culture. Though each system is different, all of them are based on certain principles of physics, and thus contain certain patterns, intervals, and chords. It's easy to take our current tuning system for granted, but it wasn't always this way. Before we explore the different tuning systems of Western music, it's important to discuss what exactly we're tuning. Though Western music has tens, probably hundreds of unique scales, they all use only 12 unique notes. Together, these notes form the Western Chromatic scale. Looking at this diagram, you might be wondering how instruments like the piano can have more than 12 notes. The key is that the notes repeat. The 13th note of the chromatic scale, if you will, is the same as the first note, just higher. This note is a C, and this note is also a C. Pretty easy. The interval between these same notes is called an octave, and it will become important later. Now that that's out of the way, let's move on to our first tuning system, just intonation. Debatedly invented by Pythagoras, an ancient Greek mathematician and cult leader, just intonation is probably the most fundamental tuning system and is based on the harmonic series. For those of you who haven't taken a physics course recently, let me try to explain just intonation with minimal math. In order to make a sound, an object, like a string or a column of air, must vibrate in a way that forms a standing wave. Humans perceive the frequency of this vibration as pitch. The wavelength of the wave on the string is inversely proportional to its frequency, meaning, more simply, that a longer wavelength creates a lower pitch. In fact, this relationship can be defined by the simple equation speed equals frequency times wavelength. Because the speed of sound is somewhat constant, you can calculate the wavelength using the frequency, and vice versa. Anyway, the simplest standing wave that a string can make has a note at each end with the entire length of the string vibrating in between. In this configuration, the string is half as long as the wavelength. This wave, and the pitch that it produces, is called the fundamental, and is the lowest frequency that the string can produce. It is also by far the loudest note, and is therefore the one associated with the string. However, this string can produce many more notes, all of which are higher and much quieter than the fundamental. A standing wave can have 3, 4, or really any number of notes that you want. Because each of these configurations has different wavelengths, each one produces a different pitch, which relates to the fundamental by a simple ratio. First, the second harmonic produces a pitch twice as high as the fundamental because the wavelength is half as long. Accordingly, the ratio between the two frequencies is 2 to 1. The third harmonic has a ratio of 3 to 2 to the second harmonic, and the fourth harmonic has a ratio of 4 to 3 to the third harmonic. This pattern continues forever, and in aggregate is called the harmonic series. When a string is plucked, all of the notes of the harmonic series sound at different volumes. Though the upper harmonics get drowned out by the fundamental, they still give a string its distinct sound, or timbre. Now, it's important to note that the human ear tends to hear simple ratios between frequencies as consonant, or in tune, and more complex ratios as dissonant, or out of tune. Because all of the harmonic ratios are simple, by definition, they are all named intervals in Western music. The ratio of 2 to 1 is the octave that I mentioned before. The ratio of 3 to 2 is called the perfect fifth. Next comes the perfect fourth, major third, minor third, a few ratios that don't get used a lot, and finally, the major whole tone with a ratio of 9 to 8. The various methods of just intonated tuning use these intervals to construct every note in the Western chromatic scale, using a root note as the starting point. For example, using C as a root note, the frequency for G can be constructed by multiplying the frequency of C by a ratio of 3 to 2. F can be constructed by multiplying by a ratio of 4 to 3, E by multiplying by a ratio of 5 to 4, and so on. Intervals that aren't found within the harmonic series can be constructed by stacking two harmonic intervals on top of each other. Mathematically, this is done by multiplying their frequencies. It is also possible to construct every note by stacking perfect fifths. This is called Pythagorean tuning. Though this system still sees some use today, it has glaring issues that make it inapplicable to most contexts. For example, because the frequency of each note is based on its relationship to a root note, it will only sound in tune in that note's key. Take a listen to this justly intonated melody in the root key. And now, taken out of its tonal context. Sounds kind of off, doesn't it? In addition, some notes can be constructed by multiple sets of ratios. This leads to phenomena like comma pumps, which constantly inflate the pitch of melodies without technically going out of tune. it became clear that a new tuning system was necessary, so in 1584, 12-tone equal temperament was developed. Instead of being based on the ratios of the harmonic series, 12-tone equal temperament is based on dividing the octave into 12 equally spaced semitones, hence the name 12-tone equal temperament. The ratio between any two adjacent semitones is always a constant 12th root of 2. Because the 12th root of 2 is irrational, no simple intervals can exist within the system except for one, the octave. Because 12 times the 12th root of 2 is just 2, any and every pair of notes an octave apart will sound perfectly in tune. All other intervals will be slightly off, but not enough for most people to notice. Now, because the system isn't based on a root note or key, instruments capable of playing in any key became possible. Instruments like the harpsichord and later piano were invented and became widely used because of their pitch and dynamic range. The 12-tone equal tempered system served as a base for Western music from the Baroque period onward. So far, I've only covered the tuning systems used in Western classical music. It's important to recognize that other cultures have their own tuning systems. For example, the Indonesian gamelan uses the slendro and pelog scales. The Japanese hirayoshi scale uses semitones similar to those in Western equal temperament. Finally, the Arab tone system uses a subset of 24 equal temperament. This system can be thought of as adding a note in between every note in the Western chromatic scale. As of the writing of this script, 12-tone equal temperament is solidly the most widely used tuning system in Western music. It's unlikely that this will change anytime soon. Western music theory, and everything built atop it, is in turn built on 12-tone equal temperament. This hasn't stopped experimentation, though. Microtonal music, especially using the 24 equal tempered or Arab tone system, has steadily been gaining popularity in Western music. In the early to mid-20th century, composers like Bela Bartok, Charles Ives, and Pierre Boulez experimented with quarter tones in their compositions. More recently, artists like Jacob Collier have embraced quarter tone tuning in the context of popular music. Some artists have also started experimenting with other equal divisions of the octave, or Ito for short. 19 and 31 Ito are among the most popular. It's also worth noting that music outside of 12-tone equal temperament is extremely difficult to perform on traditional instruments. In fact, some instruments, like the piano, can't play microtonal music at all without serious hardware modifications. For instruments with continuous pitch ranges, like the violin and voice, it's still much harder to play in tune and requires a lot of additional practice. Because of this, most microtonal musicians record in 12-tone equal temperament and then use a digital audio workstation to change the pitch, or exclusively use virtual instruments. Because of this, it's unlikely that 24-tone equal temperament, or any other tuning system, will become dominant, no matter how awesome that would be.